You know, we all love a good backup plan, right? I mean, whether it's an extra copy of a critical file or just a spare tire in the trunk, having that fallback, it gives you some peace of mind. It's a safety net. And in our digital world, networks absolutely rely on these safety nets, these backup connections, to keep us all online. But what if that safety net, the very thing meant to save you, could actually cause a complete and total collapse?
Yeah, that's a weird question, I know. But in the world of computer networking, it's a very, very real danger. See, having a backup path is absolutely essential, but it can also create this weird paradox, a hidden flaw that can take down an entire network in the blink of an eye. Okay, let's dive into this.
So this brings us to what's known as the redundancy paradox. Now, the basic idea in network design is to get rid of any single point of failure. You always want more than one way to get from point A to point B. We call this redundancy, and it is the bedrock of a reliable network. But there's a catch. On one hand, redundancy is awesome. It gives you what's called fault tolerance. That just means if one connection goes down, traffic just takes the other route. Simple. No disruption, everybody's happy. But on the flip side, in the world of our local networks, what we geeks call layer 2, where devices are talking directly to each other, that same redundancy creates an absolute nightmare scenario called a layer 2 loop.
So what in the world is a layer 2 loop? Well, just imagine you have two network switches, and you connect them with two separate cables for that backup path. Now, when a piece of data, a frame, arrives at one switch, its job is to send it along. So it forwards it out the first cable and also the second one. The other switch gets it and, well, it does the exact same thing, sending it right back. The frames get trapped, bouncing between the switches forever. And here's the crazy part. Unlike internet traffic, these little frames have no expiration date, no time to live counter. They are literally going to loop until something breaks.
And that's something that breaks? Yeah, that's the entire network. So let's take a look at the anatomy of this digital meltdown, because it happens way faster than you might think.
It all kicks off with just one single, totally innocent message, specifically something called a broadcast frame. You can think of it like a computer shouting, "Is anyone out there?" into a really crowded room. Normally, this is perfectly fine. But in a network that has a loop, this is the spark that's about to light a massive fire.
So that one frame hits the loop, and it starts multiplying endlessly. We call this a broadcast storm. The switches are just instantly flooded, trying to process this infinite wave of traffic. Their internal address books, their MAC address tables, go haywire because they see the same devices popping up from multiple directions all at once. The connections get totally saturated, the processors on the switches spike to 100%, and just like that, total network failure.
And I'm not talking about a slowdown here. This is a complete, lights-out network outage in a matter of seconds, all because we tried to build in a safety net. So the big question is, how do we get the benefit of having a backup plan without, risking a catastrophic meltdown?
Well, we need a hero. We need an intelligent protocol, something designed specifically to hunt down and slay these loops while keeping our precious backup paths safe and sound.
And that hero has a name, the Spanning Tree Protocol, or STP for short. It all started with this 1985 paper by the brilliant Radia Perlman. She came up with the core algorithm that allows networks to be both redundant and stable. Just a true stroke of genius.
And here is the core idea of STP, and it's just so clever. It doesn't tell you to unplug the backup cables, no. Instead, it creates this clean, loop-free logical map of the network. It intelligently finds any of those extra paths that could cause a loop and puts them into a blocking state. They're still there, physically connected, ready and waiting, but they are not allowed to forward any traffic. Not yet, anyway. So how does it do all this? I mean, how does a bunch of switches with no one in charge agree on which paths to block? Well, it's pretty cool, actually. They hold an election. It's this fascinating four-step democratic process that lets the network organize itself.
Okay, so here's the quick overview. First, the switches elect a leader, which they call the root bridge. Then, every other switch figures out its single best, fastest path to get to that leader. After that, they all agree on which ports are officially allowed to forward traffic. And the final step? They block every single other path to make absolutely sure there are no loops.
All right, step 1, the election. As soon as you power these switches on, they start sending out these special messages to each other. Every switch has a unique ID, kind of like a candidate number in an election. And the rule is simple. The switch with the lowest ID wins. So in this picture, S1 has the lowest ID, so it becomes the root bridge, basically the boss of the whole network.
So, once the boss is chosen, every other switch has one job.
figure out its single most efficient path to reach that root bridge. The port on the switch that leads down that best path gets a special title, the root port. You can think of it like every employee figuring out the absolute fastest hallway to get to the CEO's office.
Okay, so for the final steps, on every single cable that connects two switches, they have a quick chat and agree on which end is going to be in charge of forwarding traffic. That winning port becomes the designated port. Now, any port that isn't a root port or a designated port, well, that's a backup path. And to stop a loop before it starts, STP puts all those extra ports into a blocking state.
And voila, this is the end result, a perfectly stable, completely loop-free network. See that little orange light on the port connecting S2 and S3? That means that link is logically blocked. No data can pass through it. So now we have our backup path, our redundancy, but with zero risk of a broadcast storm. The paradox is solved. But what's the real payoff here?
Because the true magic of STP isn't just about preventing loops in the first place. It's about what happens when things actually go wrong. This is where our backup plan finally gets to be the hero.
Okay, look at this. On the left, you've got our happy, healthy network with its backup link safely blocked. But on the right, disaster. The main link between S1 and S2 just failed. Now without STP, half the network would just be offline. But with STP, the switches sense that failure instantly. The protocol automatically recalculates everything, unblocks that backup path it was saving, and within seconds, traffic is flowing again through the alternate route. And this is the most important part. The network literally heals itself. The switchover is so fast that for the actual people using the network, you, me, nothing happened. Your video call didn't drop, your file transfer didn't fail. STP just worked silently in the background, our invisible guardian, making sure the network just stayed on.
It really makes you think, doesn't it? Spanning Tree Protocol is just one of dozens of these silent, automated systems that are working flawlessly every second of every day just to keep our interconnected world running. And it kind of begs the question, what other invisible guardians are out there, quietly preventing digital collapse right under our noses?